Hi, welcome to the first lesson on topic 12, magnetism and the motor effect. This lesson is about magnets and magnetic fields. Now, magnets are fascinating objects and are used throughout our day-to-day lives and also in many ways we really don't expect. They're used in hard drives, in our computers, in compasses, in headphones, speakers, electric motors. They're often used in turbines, as well as in maglev or magnetic levitation trains. If you recall your Key Stage 3 learning, you'll remember that a magnet has a north and south pole, like so. Decide whether or not these magnets will attract or repel. Pause the video and have a go. So, in the first case, we have two north poles facing each other. These will repel. Below that, we have two south poles, and these will also repel. Next, we have a south and north pole, and these will attract. And finally, we have a north and south pole, and these will also attract. So we can clearly see that like poles repel, like poles being north and south will repel, and opposite poles attract. Now, we generally associate magnetic materials with metals, but not all metals are magnetic. Of the group of metals we have here, how could we test whether they're magnetic or not? Well, all we'd need to do is bring them in the presence of a permanent magnet like so. And very quickly, we would see that iron, nickel, and cobalt are magnetic. Steel is also magnetic, and that's because it's predominantly made of iron. Here we have a very interesting image. We have a permanent magnet and a series of paper clips. Now, these paper clips are not magnetic materials, yet they're being held up using magnetic force. How does this happen? Pause the video and think. Interestingly, the North Pole here induces a South Pole right below it. This therefore induces a North Pole below that, and so on. This allows the paper clips to be attracted to one another and be held up by the permanent magnet. This is called induced magnetism and continues from paperclip to paperclip. It should be mentioned that this only happens within the magnetic field of the permanent magnet. Next, based on the previous picture, have a go at matching the term on the left to the definition on the right. Pause the video and have a go, and don't forget to write these down. So you should have identified that a permanent magnet is a magnet that always creates a magnetic field, the key word being always. A temporary magnet is the name of any magnet that can stop being magnetic. It could either be an induced magnet or an electromagnet, and we'll learn about electromagnets in the coming lessons. And finally, an induced magnet is when a magnetic material is in a magnetic field and therefore becomes a magnet itself. And it stops being magnetic when it is out of the magnetic field, just like the paper clips we saw before. Now, we've learned about permanent magnets, induced magnets, and temporary magnets. But a magnet is simply a material which has its component atoms ordered in a way that the material produces a magnetic field. Now, I know what you're thinking. What's a magnetic field? A magnetic field is a region of space around a magnet where magnetic materials or current-carrying wires, which we will learn about in the coming lessons, will experience a non-contact force. Remember, magnetic force is a non-contact force. Now, what does a magnetic field look like? Here we have a simple bar magnet. Very carefully pay attention to how I draw out these lines, the magnetic field lines. I follow 4 rules. Let's see if you can identify what they are. It's extremely important that you follow these rules when drawing magnetic field lines. The rules are that the magnetic field lines always point from north to south. They go out from north and in to the South Pole. Next, we can see that the magnetic field lines are far closer at the poles and much further apart away from the poles. And finally, magnetic field lines never overlap. Now, based on this diagram, where's the magnetic field the strongest? Pause the video and think. Clearly, we can see that the magnetic field is strongest at the poles. We can see that because the magnetic field lines are closest together at this point. And it's much weaker away from the poles, as the magnetic field lines are much further apart. Let's look at some applications of magnetic fields in different situations. This is a very common image that you would have seen at Key Stage 3 or in school. This is an image created using a bar magnet, a piece of paper, and iron filings. It's a very common exam question, and we can see that the iron filings have aligned themselves along the magnetic field lines. We can also see that the concentration of iron filings are strongest at the poles. This supports what we said earlier. Magnetic field lines can also be represented using compasses, where we can see that the compass will always point in the direction of the South Pole from north to south. We can often use compasses to draw magnetic field lines by using lots of compasses in different points around a bar magnet. And finally, magnetic field lines are certainly present around the Earth. You can certainly see this if you use a compass. But why do you think the Earth actually has a magnetic field? Think back to the magnetic materials we spoke about earlier. It's actually because the core of the Earth is made of nickel and iron magnetic materials. And as a result, the movement of the nickel and iron in the Earth's core causes the Earth to have a magnetic field. I hope this has been useful. If you have any questions, please do ask.